I think we can get started with the lecture. And today, okay, we're going to do a little bit more math. We're going to talk about Riemannian metrics and geodesics. Okay, so obviously we're going to see what it means and all that, but I think it's important to just see a few equations, see a few formulas, and try to demystify this a little bit. Otherwise, if I only present to you pictures and all that, every time you open a book and you see a Riemannian metric, you're going to close it back down, and you're going to miss a lot of insights. So the idea here is to get in a little bit into the core subject. So just as a recap of the previous lectures, okay, we saw that our main aim, okay, at the MVA in general is to mitigate the curse of dimensionality. Okay, be able to do interesting statistics when we have way more columns than we have rows, okay, in our data sets. So lecture 2, we saw that the best case scenario is when you have an expert at hand that can provide to you high quality features. Okay, and if you are in a setting where you have maybe quite a few columns, but you know what they mean, basically they are very good discriminants for your classification or regression problem, then probably you can just choose a standard baseline from the 80s, 90s, something that is extremely well understood, like a tree. Okay, a regression, a kernel regression method is going to work, maybe. And so, okay, it's important to start with the basics. Then we see that maybe if you don't have access to super high quality features, maybe instead you can specify a relevant family of functions, okay, for your problem, a relevant family of estimators, and then try to solve a regression problem where you find optimal parameters that describe your function that fit the data set as well as you can. So first baseline is to use kernel methods. Okay, we saw what it means to use Gaussians, these kind of things. Or in fields that have a long history, like imaging sciences, we know that for a large class of problem, we should use a convolutional architecture. Okay, and so back in the days, people could only fit maybe 10, maybe 100 parameters, but now we have GPUs, okay, we can fit thousands, billions of parameters, and that's what we call doing deep learning. Finally, maybe in other settings, instead of having access to a relevant family of functions, it's more that you have access to relevant neighborhood structures that may be given to you, or that may be the only thing you can leverage out of your structure. Like the only thing you can do with your data set is compute a k-nearest neighbor graph, because otherwise you have zero faith in the numerical value as in your table. And this is what we call, okay, doing graphs, neural networks, etc. So we see that in this whole project, in this whole pipeline, our main challenge, as academics, as mathematicians maybe, is to allow people to go from local implementations to global understandings. Okay, we try as scientists in this community to understand what happens when people say that they work with a graph. Because when people say they work with a graph, they just see edges. When people work with kernels, they just see a formula. And it provides us, okay, it's good enough to implement things, but it's clearly not good enough to understand what is happening. And so that's why we try to unzoom, try to understand global structures that are defined by those atomic interactions. A bit like in chemistry, you know what happens when two water molecules collide, but you don't really understand what happens with the fluid. Okay, so we try to put out of this scientific understanding, we try to produce guidelines and insight for practitioners in return. And so you have very nice, ideally a virtuous cycle between people who try things, we also try things, but we provide complementary understanding of all those models that people have been implementing for decades. So now, maybe the main insight that I wanted to push, over the last 2 sessions is that large graphs are best understood as continuous objects, at least some large graphs, not all of them. Okay, why? That's because probably when you learn about graphs at school, in prépa, in école d'ingénieur, we like to present them as discrete objects. Maybe we say we have 6 nodes, 100 nodes, some edges. But then we saw that if you have thousands, millions of nodes, probably still trying to understand this very low grain structure doesn't allow you to capture the intrinsic structure of this metric space. Okay, and that's why we talk so often of the manifold hypothesis. Okay, in machine learning. So a manifold it just means like a generalized surface. Okay, it's just something that is locally a metric space that locally looks like a vector space, and that's it. Okay, so think your surface, but in high dimension. And obviously, whenever we get a data set in our hands, it's never a manifold. Okay, it's always something sampled. You cannot expect it to be a real surface or a real 3D space embedded in dimension 10. But having this perspective that this kind of sampled Swiss roll is under the hood of the surface definitely allows us to come up with interesting algorithms. Okay, and this is what our job is all about. So that's for real data set. And finally, sometimes the graphs that we are given actually come from a physical surface, like a physical manifold, and that's very often the case in 3D shape processing, which is my field of origin. We have genuine physical objects that are discretized and presented to us as meshes. But obviously, if you want to understand it as a network instead of understanding as a surface, then you're going to fall into many traps related to sampling densities, etc. So this is the idea that people try to push in machine learning now, and it's a story that it's an idea that has very long history in physics. Okay, maybe I don't know, but in France, typically people who do machine learning started by doing a little bit of physics. So that back in the days of Kepler, Newton, people were understanding the solar system as a collection of like a handful of point masses, and people were able to do physics with those systems. Back in high school, we were studying the interaction between the sun and the Earth, and if you say that you only have two objects that interact with each other with the gravitational force, then you know that essentially the Earth makes an ellipse around the sun. So that's the idea. And then, okay, this was kind of a more or less a solved problem, even in the 18th century. And then people started to be interested in maybe more complex objects, maybe smaller objects, but complex objects like gases or fluids. Okay. And there, the main insight, of all the science from the 19th century, from all this physics, mathematical physics, in the 19th century is that you can try to describe like a gas as a big collection of particles that interact with each other with very simple form. And for very simple models, like the Boltzmann ideal gas model, you can get away with a discrete description and recover, using physical statistical methods, you recover the actual macroscopic laws of gases. So that's really a great success to be able to go from the microscopic to the macroscopic level using only math. But then, if you try to simulate liquid gases, like non-ideal gas models, like trying to make cool simulations or just simulations for engineering, basically you have to start looking at your fluid as a continuum. Okay, and this is what our intuition tells us. Maybe it's our mammal brain evolved after millions of years, that whenever we look at time, or whenever we look at just a glass of water, we like to think that it's a continuum, and so we have to work with continuum mathematics, and that's why it's a little bit more challenging, because we cannot work with vectors anymore. We have to work with functions. Okay, and a function is just a vector with an infinite number of coordinates, because for every value of x, you have a different coordinate, f of x. And that's why, so we're going to talk about it in the next lecture, but that's why we always think that working with probability distributions or functions, it's like doing geometry or linear algebra in a space that has an infinite number of dimensions. That's what makes it challenging. So, okay, that's the story. Essentially, we are going to do a little bit of math that allow us to push this discrete to continuum program. And this is going to rely a lot on ideas from the 19th century or from the 1950s. And that's because, as I told you, even if those problems are relatively new in machine learning, because it's relatively new that we're able to deal with millions or billions of points. In physics, it's been the case for 150 years, 200 years. So, there's a lot of background. We should definitely look what mathematicians and physicists have in their treasure chest for us. So today, we're going to talk about going from discrete graphs to continuous spaces. So we're going to describe continuous spaces that are not just vector Euclidean spaces. So we're going to spend like half of the lecture just on the Poincaré disk. So maybe the most archetypal example of a space which is not Euclidean, but that you can describe using high school level math. And then talk a little bit about local metrics and geodesics, in the general case, but without going too far, and hopefully make a lab session, with a library that implements all of that. Then next session, we're going to talk about this discrete to continuum travel, but more in the setting of probability distribution. So we're going to talk about what happens when you try to understand a very large discrete sample as a continuous distribution. Okay, so we're going to talk about the main insight that come from the 1950s, like this duality between distributions and continuous functions. Talk about what mathematicians call dual norms, but what people in machine learning now call like adversarial games or adversarial norms. And talk about the three main geometric structure that we like to put on continuous distribution, namely like information geometry that comes from everything that has entropy in the name, like relative entropy, cross entropy. Then about kernels that are related to everything that people call like Sobolev norm, Hilbert norms, those kind of things. And finally, optimal transport, so everything related to Wasserstein, blah, blah, blah. Okay, and finally, in the last section, which is more like cultural material, but very important, I think, cultural background. Okay, I put it at the end because you don't have to recap this for the exam. We're going to talk about hardware bottlenecks, like how else do you implement those things, those continuous geometric algorithms on a real computer. Okay, and then you have to ask yourself questions about memory management, registers, parallel course compilers, and maybe try to just look at the hardware industry right now, understand the current trends, and see how it's probably going to impact our field over the next few years. So, okay, and before jumping into it, now it's going to be, we are going to try to make at least one proof, and making a proof, on PowerPoint and Beamer, it's really not ideal, so I have to skip things, and I understand that this may sound a little bit shaky to you, and so that's why I would like to recommend, those references if you're really interested in everything we're going to talk about in the next 3 lectures. I think you can have a look, at these books. So first, you have some textbooks and introductions in English. So first, like it's kind of the outreach paper by Etienne Gis, like Poincaré and his disk. And then very nice mathematical introduction to the Poincaré disk, which is called Hyperbolic Geometry by Cannon and like a few other authors from actually 25 years ago. And the main proof that we're going to make today comes straight from this paper. Then, if you really want to go deeper, not just into simple Poincaré toy models, but into real Riemannian geometry, you can look at this textbook, like Riemannian Geometry and Introduction to Curvature, which is pretty nice. And if you go on my website in French, there is actually a kind of rehash of its content that is called Introduction à la géométrie riemannienne par l'étude des espaces de forme. Okay, so it's kind of lecture notes for a class that I was giving at the École Normale Supérieure around 2016. Okay, and finally, especially for everything that's related to applied Riemannian geometry and probability distributions, you can look at my PhD thesis, geometric data analysis beyond convolutions. I'm really trying to make it very accessible, and obviously it fits well with the rest of the class, because I try to put what I think is extremely relevant if you want to do geometry in this field. Okay, so that's about it for English material. And finally, another set of lecture notes that I wrote at the École Normale Supérieure, just culture mathématique. You have 2-3 chapters on Riemannian geometry. I think they're very accessible, because it was a lecture that I wrote for students at the ENS who are not from the math department, like philosophy, computer scientists, historians, everyone who is interested in math but doesn't necessarily have all the background on that. Okay, So now that I got this out of the way, let's start by looking at this space that's called the Poincaré disk. And just out of curiosity, I won't assume anything, but have you ever heard about it or just saw an illustration of it or never? Like it's completely brand new for you. Okay, okay.
Just an illustration.
Okay. So it's super brand new then. Okay, but it's interesting because it's the kind of thing that if you go in the math degree at university or in one of the écoles normales, typically you do a little bit of that in like in undergrad. So just to tell you that this is totally mainstream for mathematicians. So it's part of this virtual field we are completely embedded in, but obviously it doesn't really percolate outside of that. So okay, good. So first, okay, it's called the Poincaré disk, mainly because Henri Poincaré, a famous mathematician from 150 years ago, talked a lot about it. And so we're going to start just by looking at a big quote, at an extract from an outreach book by Henri Poincaré, which is called La science et l'hypothèse, so Science and Hypothesis. Basically, it was just a book it was mostly about philosophy, actually. But in this book, you have like in chapter 3 or 4, you have a long explanation just of how on earth can we even start dealing with non-Euclidean geometries. And just Euclidean, it just means, standard vector space, Pythagorean theorem, straight lines are geodesics, these kind of things. Okay, just in case it wasn't clear. Okay, so let's start. So it's really the start of, I think, chapter 3, the non-Euclidean world. Okay, if geometrical space were a framework imposed on each of our representations, considered individually, it would be impossible to represent to ourselves an image without this framework, and we should be quite unable to change our geometry. So that's just first remark, is that if, because we are so used to this Cartesian representation of geometry, we like to think that we live in a 3D space, you have reference points, X, Y, Z, axes, coordinates, okay, and this is what we call Euclidean geometry. And Poincaré just remarks that, okay, those axes, they do not exist in real life, okay? They are not there. Whenever we take a picture, we do not see those axes. So it's purely an a posteriori mathematical model of what happens. But just to start that those axes, they are not real, or they have no physical reality. And so maybe we can do geometry without them. Okay, they are not as physical as mass. This is not okay. So, but this is not the case. Okay, those axes, they do not actually jump into your face every time you look at the 3D space. Geometry, it's only the summary of the laws by which these images succeed each other. Okay, and so here, I make to you a small illustration. Basically, when we deal with Euclidean geometry, when we try to say that whenever you take a triangle, then the sum of their angles make 180 degrees. What we are really saying is that it's a common fact, at least at our scale, like in this room, that if I stay here, at one place and I make 3 steps, then I turn by 120 degrees. I make 3 steps, then I turn by 120 degrees and I make 3 steps. I'm back at my original position. Okay, like basically this thing about triangles geometry, it's not something that has a physical reality, but it's more a kinematic observation about the real world. Okay, because this is true, because when I have a pen and I draw a triangle, I go in 3 straight lines with those 3 angles. I come back at my original position. Okay, this is why Euclid and all those people try to capture with this idea of Euclidean geometry. And so, okay, that's fine. But now you see that now that we understand that geometry is more about movies than they are about still frames, okay, there is nothing, therefore, to prevent us from imagining a series of representations, so a movie, similar in every way to our ordinary representations, but succeeding one another according to laws which differ from those to which we are accustomed. Okay, and so that's what I'm displaying here. As we understand that geometry primarily about movies, then you can totally imagine that it would be possible to construct a sequence of frames such that, okay, you make 1, 2, 3 steps, then you turn right by 120 degrees, then 1, 2, 3 steps, then you turn right by 120 degrees, 1, 2, 3 steps in straight line, but you do not end up on the same point as 0. Okay, like it's totally possible to imagine that, and actually you have video games, where it's the case, like funny simulators that simulate non-Euclidean geometries. And like, I don't know if Portal, I never played it, but you maybe have those kind of ideas in those types of games. Okay, and so we made us conceive, like it's not inconceivable. Obviously, we'll have to make it work. We'll have to propose a model, but just as a first remark, you can imagine that beings whose education has taken place in a medium in which those laws would be so different might have a very different geometry from ours. Okay, and all this discussion, it takes place at a time, or a generation after, a time where people were obsessed with the idea of, is Euclidean geometry the only geometry that is self-consistent? Okay, and that's why in the history of mathematics, in the 1860s, people came up with other models of geometry that did not obey the same laws, but that were just as consistent. Okay, and that's where this comes from. And that's why it starts with philosophy. Okay, and so now Poincaré proposed to us a model that behaves more like this than like this. Okay, a model in which triangles are weird. Okay, and so suppose, for example, a world enclosed in a large sphere. So for us, it's just going to be a large 2D disk, and subject to the following laws. So first, the temperature is not uniform. It is greatest at the center, so here you're hot, and gradually decreases as we move toward the circumference of the sphere, where it is absolute 0. Okay, so you just imagine a disk. In everything we're going to do next, it's a disk with radius 1, so just a unit disk. And you assume that here, essentially, the temperature is like 1 or 100 Kelvin. And here it's 0, and then it decreases. So whenever you try to approach, whenever you try to reach the boundary of this disk, you get colder and colder. Oops. So the law of this temperature is as follows. If r be the radius of the sphere, so for us it's just going to be 1, and small r, the distance of the point considered from the center, then the absolute temperature will be proportional to R2 minus R2. So just to be clear here, if big R is equal to 1, small r is equal to 0. Okay, and so this is the temperature is here, it's 1 minus 0, so 1 Kelvin. Okay, we normalize things. Then here, okay, if I'm halfway through from my outside perspective, if I'm halfway through, small r is equal to 0.5. Small r squared, it's equal to 0.25. And so the temperature, it's 0.75 Kelvin. And then, as I approach here, small r gets closer and closer to 1. And so the temperature gets closer and closer to 0. So that's just first how we're going to construct a field of temperature. And as we see, this is what we call a Riemannian metric. Okay, Riemannian metric, simple Riemannian metric is just a field of temperature. And now, okay, to relate temperature to physical distances, Poincaré imagines a world where further, I shall suppose that in this world, all bodies have the same coefficient of dilatation, so that the linear dilatation of any body is proportional to its absolute temperature. Okay, so you imagine that if it's twice as cold, you are twice as small. Real physical objects do not behave like that, because you have like an incompressible limit. At 0 Kelvin, objects do not really shrink, but you can imagine that you have found like maybe an ideal gas, something like that actually behaves in this way. And finally, you assume that a body that is transported from one point to another of different temperature is instantaneously in thermal equilibrium with its new environment. Okay, so just you cannot be still hot, move, be still big, but in the cold space, you assume that basically the temperature gives you immediately changes your scale, and so immediately, basically the temperature of the world immediately affects your temperature of your body, and so immediately affect your scale. Okay, and this is why you can imagine. So we're going to explain, I'm going to take 1 hour to explain what everything here means. But this is why you have at least this small diagram where here you have someone who is like 1 meter tall child, and then here he's just 75 centimeters tall and progressively gets smaller and smaller. And obviously the idea is that if you're small, you make small steps. Okay. So there is nothing in this hypothesis either contradictory or unimaginable. Okay. A moving object will become smaller and smaller as it approaches the circumference of the sphere. So let us observe in the first place that although from the point of view of our ordinary geometry, this world is finite. So for us, the world, the diameter is equal to 2 because it's just a unit disk. To its inhabitants, it will appear infinite. Okay, so this, we're going to make an integral. We're going to see that it's actually infinite, but just intuitively, you can see that it's likely to be true just because when people get closer and closer, they shrink very fast. Okay, and so basically making steps after an infinite number of steps, they are still within the boundaries of the circles. Okay, if the temperature decreases fast enough. So as they approach the surface of the sphere, they become colder and at the same time smaller and smaller. The steps that they take are therefore also smaller and smaller so that they can never reach the boundary of the sphere. So it's a kind of strange space in which the Zeno's paradox is actually true. It's actually interesting. So, okay, that was what Poincaré was writing in his philosophy book. And so now let's look at what you actually write, okay, in a mathematical textbook. And so if you want to turn those words into formulas, we can say that the Poincaré metric is what mathematicians call a Riemannian metric after Bernard Riemann. And so locally, a small Euclidean metric with a scaling factor. So here, so we assume that we are working in the unit disk, so with points that have coordinates x and y, such that x squared plus y squared is strictly smaller than 1. So that's just the squared Euclidean norm. And then we are going to decide that the distance between a point xy and a point xy plus, a small velocity vector like dx plus dy, if dx and dy is infinity, very, very small, is equal to this formula, and we're going to explain where this formula comes from. It's equal to 2 times the Euclidean norm of the vector dx dy divided by 1 minus x squared plus y squared. So the factor 1 minus x squared plus y squared is the temperature, okay, that we were talking about. And so when I divide the extrinsic Euclidean norm by this temperature, what I'm really saying is that since a small man or small woman at location xy has an intrinsic scale of 1 minus x squared plus y squared, then with respect to this intrinsic perspective, this vector here, xy, has a scale which is the extrinsic norm divided by my intrinsic scale. Okay, and so if it's colder, so if 1 minus x squared plus y squared is small, then this vector has a much larger intrinsic length than it looks to us from the outside. Okay, so that's just that's exactly the reformulation of those equations, of those words. So that's for the distance, and I put a factor 2 because, as you'll see later, it makes a factor 1 in other representations of the Poincaré space. Okay, so that's our local length element. So you see that, for instance, in the center of the disk, x and y are equal to 0. And so 1 minus x squared plus y squared is equal to 1. And so up to a factor 2, my metric is exactly the Euclidean metric. Okay, so in the neighborhood of the center, the length that you measure with your outside ruler are exactly the same as the length that people inside the disk would measure. But here, okay, you have this temperature factor that messes up everything and makes the intrinsic distance much larger than they appear to us. So that's for the length element, but you see that if I want, I can square this. And so I say that the square distance between xy and x plus dx, y plus dy, it's this formula. So 4 dx squared plus dy squared divided by the temperature squared. Okay, and so usually, okay, it's not going to matter in this lecture, but just know that usually people prefer this formula over this one. Okay, because here you have a square root. It's a bit annoying here. It's just squared, just a simple squared. It's a quadratic form. Okay, you can represent it using a matrix. So people say that this squared Euclidean, this squared symmetric matrix is what we call the Riemannian metric of the space, and we use those notations. So we have the squared norm of dx dy, but at location xy, we say that, okay, it's a dot product between dx dy and dx dy, but with here a matrix which is not necessarily the identity. Okay, for the Euclidean norm, the squared Euclidean norm is just dx dy dot product with dx dy. And here we have distorted things by adding a square matrix, which is here a 2 by 2 square matrix with the coefficients that are given in this formula. So 4 divided by the temperature squared, and so you this formula. Okay, and that's why if you go in Wikipedia and look about Riemannian metrics, they are going to talk about matrices, okay, a field of matrices that locally defines a Euclidean metric. But okay, you can just have in mind that it's just a way of locally scaling the Euclidean metric. So that's for the first formula. And then now that we have this formula, okay, maybe I should encourage you to write it down, okay, because I cannot keep it in every slide. So the distance between xy and x plus dx, y plus dy, locally it's 2 times the Euclidean length of dx dy divided by the temperature. So y minus x squared plus y squared. Okay, and now that we have this formula, we understand what it means. We are going to try to actually compute the length of the segment from the center of the circle to the boundary and see that it's actually infinite from the intrinsic perspective. So that was our formula. And now let us consider a path, okay, a very smooth path from the interval 0, 1 to the unit disk. So let's say just this path. And whenever we have a path like that, we can define its Riemannian length. Okay, the length is just going to be the integral of the length of the norm of the velocity vector. Okay, that's what you do in Euclidean space. And here the only twist is that the norm, the length of the velocity vector is going to be computed using the local metric. Okay, so that's really a way of computing the intrinsic distance for inhabitants of this disk world. Okay, now for the straight path. Okay, so that's just this one. So the coordinates for a point gamma of t like xy are going to just be t0. So x goes from 0 to 1 and y doesn't change. And now the length of gamma. So I just use the same formula. It's the integral between 0 and 1 of the norm of the velocity vector. So the velocity vector, it's always 1, 0 in my extrinsic coordinates. So the norm of 1, 0 divided by, not divided, but at location t0. And I integrate that for t that goes from 0 to 1. So that's my that's a just copy paste of this formula. And now if I come back to the formula for my metric, then this vector 1, 0, its Euclidean norm is always equal to 1. So I have 2 times 1 divided by 1 minus the temperature at time t. And so temperature at time t is just 1 minus t squared. And so the intrinsic length of this curve for the Riemannian metric is the integral from 0 to 1 of 2 divided by 1 minus t squared. And now, even if you have forgotten how it works, from prépa, you know that you can factor this 1 minus t squared into 1 plus t, 1 minus t. And so you have the integral from 0 to 1 of 2 divided by 1 plus t times 2 divided by 1 minus t. And so the term in 2 divided by 1 plus t, it's fine, it's just 2 divided by 2, so nothing special. But the 2 divided by 1 minus t, it explodes just like the function 1 over x. And so you know that the area under the curve of 1 over x is plus infinity. Okay, and so that's why we have this kind of Zeno's paradox thing, where the lengths of the steps get smaller and smaller, and the formulas have been chosen just so that we actually get plus infinity. You cannot reach the boundary of the sphere. And so that's why you can think that this Poincaré disk, it's a complete universe, but in a nutshell. Or alternatively, maybe it's more effective to think of it this way. You have the Poincaré disk, which is a space, and this disk representation is just like a lens on this space. It's just one way of representing this infinite space, of compressing this infinite space into a disk so that we can have a look at it. So that's for first thing. And now we say, okay, we have lots of formulas. And it would be nice if we had a geometric representation of the metric at every point. And actually it exists. It's a very standard tool in cartography. Okay. And why on earth do cartography and Riemannian, what does cartography have in common with Riemannian geometry? Well, it's just the fact that when you do cartography, you have a real Euclidean metric on the sphere that you project on planes, because your job is to design planes. And so if you want to represent the real Euclidean metric on your map, then you have to take into account this distortion. Okay, and so Riemannian metric comes up all the time in cartography. So here I'm showing to you an illustration of the Mercator projection. Okay, I assume that you know how it works. Basically, we have the sphere, and we assume that we have a source of light right in the center of the Earth, and that we have a cylinder, okay, that touches the sphere at the equator, that has a north-south axis. And now, using this source of light, we can define a bijection between the sphere without the north and south poles and the infinite cylinder. Okay. So that's what we call a simple cylindrical projection. And then you just unwrap and you get this Mercator projection. And then, obviously, what you see, at least intuitively, is that around here, around the equator, the distances are very well preserved. That's because your projection, it's nearly the identity. Whereas essentially close to our latitude, close to, let's say, Paris, you have a relative, using just Thales' theorem, you get that a relatively small distance in Paris gets mapped to a larger distance on the map. And that's even more true in Greenland. Okay, and that's why on those pictures, Greenland looks so big, looks so huge, whereas it's not in real life, just due to distortion. And so what cartographers use to make this explicit is that they like to display at every location, look at a set of sample location, unit balls for the actual metric, for the real metric on the Earth. So here, basically, it looks like a ball with diameter that is equal to maybe 1,000 kilometers, something like that. And so at every location, you can display it. Okay, so I mean, it's not hard. And cartographers call that the Tissot indicatrix. So Tissot's indicatrix at location xy, it's a unit ball for this local metric, or a scaled unit ball. And so in the general case, it's an ellipsoid. Okay, because in the general case, you can imagine this projection that distorts more one direction over the other. But for all the metrics and projection that we are going to see today, it's always going to be a sphere. And essentially, that's thanks to the properties of this projection method. Like stereographic projection has this property that if you have a sphere on the basically a unit ball on the sphere looks like a disk, and a stereographic projection maps disks onto disks, and that's why all the metrics that we have do not distort angles, just distort lengths. Okay, and so those unit balls, those are just glyphs, but they fully describe a Riemannian metric, because if at every point you know what a unit ball looks like, then at every point you actually have a distance. Okay. So it's completely equivalent, and maybe it's much easier to make reasonings or to think about geometry in terms of dilations of unit balls than it is to think in terms of matrices. It's up to you. Both are important. Okay, so that's one thing. I don't know how hard it is for you. Already 44 minutes. Yeah, I think we can push on a little bit, but yeah, I plan to make a break after proof on Poincaré segment. I think we'll make a break in between. Okay, so now the main spirit is that maybe this story about the Tissot's indicatrix, it's very inspiring because it allows us to see that we can represent the same metric space on two different domains. Okay, the Earth, you can represent it as a surface in 3D or on a plane, and that's the Mercator projection or any other projection. So maybe you want to do the same thing with our Poincaré disk, because the disk is fine, but maybe it's a bit cumbersome. This equation, I don't like that. I would prefer a simpler equation on another domain. And so that's what we do. And first, we're going to do it with a one-dimensional equivalent of the Poincaré disk that I'm just going to call the Poincaré segment. So Poincaré segment is just the unit ball in dimension 1, so just the segment -1 + 1. And the equivalent of my metric, 2 times the Euclidean metric divided by the temperature, on the segment, it's just written this way. So the local norm of velocity dx at location x in the segment is going to be defined as 2 times the absolute value of dx divided by 1 minus x squared. So this 1 minus x squared, here and there, close to -1, close to +1, it's still equal to 0, and so the temperature shrinks, the distance blow up. So that's the first domain, and then I propose to you to define 2 other domains. So a half disk J, a half circle, and a half line H. Okay, and the thing is that using just stereographic projections, I can define a bijection between those domains. So to map the segment onto the half circle, I can trace ray of lights that originate from this point, 0, -1. And that's what I'm displaying here. So if you just trace space of lights here, so you actually define a bijection between the segment and the half circle. So those limit points get together. The limit point +1 also stays put. But for instance, the center of the segment gets mapped to the center of the half circle, to the uppermost point, etc. And then using a stereographic projection with respect to this point, I can also map the half circle onto the half line. So here, basically, the limit point also stays put, but for instance, the uppermost point, so like the center of my Poincaré segment, was mapped to the north pole of my half circle. And now it gets mapped to a point that has a coordinate z, which is equal to 2. Okay, just by Thalès theorem. Okay, because this point has a coordinate z, which is equal to 1. And so this is equal to 2. Okay, and just so to be consistent across the different slides, okay, I'm always going to refer to like the altitude as z, and x is going to be these coordinates. So now those are just bijections, but essentially exactly like it's exactly the same formulas as the projection that we use in cartography for the Mercator projection. So it's something that you can deal with, and you can show that if your small length element on the segment was given by this formula, then equivalent distortions of the metric can be defined on the half circle and on the half line. And they are given by these formulas. So we're going to explain why exactly those formulas are just with hands, but just to be clear on the formula, because, okay, if I just skip them as slides, it's going to be impossible to follow. So, okay, yeah.
Where's the -1, 0 going on the H?
Yes, so -1, 0, it's outside of the domain. And so on H, it goes at +infinity. So it's not included in the domain. Just like whenever I was talking about the disk, you know, the boundary doesn't really matter because you cannot reach it. You know, it's at infinite distance. So
why do we choose, what's the influence on choosing, say, I pick a 0 and something that tends towards 0 or towards infinity? Like it's going to map a lot of points on the side, nothing. I don't know if you see what I mean, but basically what's the importance of picking like -1? Does it changes the the formulae?
You mean why I did choose this specific point for the projection?
I mean, this one I can see because, well,
and this one not so much.
This one, yeah, you are more free to choose.
Yes, no, so completely right. It's just because, okay, so this is the formula, and if I had chosen different points, I would have gotten different formulas for the equivalent distances, and notably this formula is extremely nice. Okay, we're going to make all the proof with this formula. So just the formula that on the line, it's basically the metric is just the Euclidean metric divided by z. You know, it's really, really good looking. So, okay, that's the only reason. Okay, well chosen points so that the formulas end up looking good. But you could pick anything else. Okay, so just to be clear, on the segment, I have one coordinate. I call it x, and essentially the temperature is 1 minus x squared. So the length element is 2 times the absolute value of dx divided by 1 minus x squared. Now, on the half circle, I have 2 coordinates, and I call them x and z. And now, so the Euclidean metric on the Euclidean length element is just the square root of dx squared plus dz squared. That's a Pythagorean theorem. And basically now, the new distance is exactly this one divided by z. So you remember how close to the center of the Poincaré disk, or here the Poincaré segment, the Poincaré metric was equivalent to the Euclidean metric because the temperature was 0, or the temperature was 1. Well, here it's the same thing, because at the top of the half circle, z is equal to 1, and so you get square root of dx squared plus dz squared divided by z. Okay, whereas here, you know, the boundaries of the segment gets mapped on the sphere to points that are close to the horizontal axis, and so you have small z, and this is why it's divided by z. And finally, when you have this metric and you project it onto the hyperbolic plane or the hyperbolic half line, we get this metric, which is just the normal Euclidean metric divided by the altitude z. Okay, so those are just formulas, and I'm just showing to you small examples to see why those formula at least make sense. Okay, like why is there a factor of 2 here and not here and there? Okay. So to understand that, maybe I can look at the simplest point in all of the model, which is the center. Okay, so the center of the disk, so the center of the segment, which is mapped to the center of the half circle, which is mapped to this point at, with coordinate 2 on the half line. And now imagine that I had a small length element, d, like a small velocity vector d here. Now, by Thales' theorem, because the distance from the source of light to the green point is twice as large as the distance from the source of light to the center of the segment, the equivalent velocity vector is going to have Euclidean length 2 times d. And now, especially if d is very small, you can also, so if d is extremely small, you can show that this length is going to be equal to this length. And now, using again Thales' theorem, you can show that the distance, the equivalent velocity vector, so the equivalent displacement, is going to have a Euclidean length, which is equal to 4 times d. Okay, so here we've just seen that our bijections, our projections, they define bijections between points, but they also implicitly define correspondences between velocity vectors, between displacements. And now we want, like, that's the way we define the matrix, the equivalent Poincaré matrix on the half circle and on the half line. We want all of those extrinsic velocity vectors to have the same intrinsic length. Okay, and so basically, this vector at location 0 should have the same Poincaré length as the vector of length 2d at location 0, 1, and should have the same Euclidean length as this vector, the same Poincaré length as this vector at location 2. And we're going to see that it works. Okay, so that's where the formulas come from. So here, this vector of length d at location 0, x is equal to 0. So 1 minus 0, it's 1. And so I get 2 times d. Okay, so the Riemannian length of this vector is 2 times d. Now, what happens here? I have a vector of Euclidean length 2 times d at an altitude z, which is equal to 1. So I recover 2 times d. So that's good. And finally, the last vector, has a Euclidean length which is 4 times d, but at an altitude which is equal to 2. And so I get 4 times d divided by 2, I get 2 times d. Okay. And so that's why those formula at least make sense. And that's also why we decided to put a 2 here. It was to get a 1 here. Because it's simpler for everything else. Okay, so that's at the center. At the center, definitely it makes sense. Now, what happens here? So here we get close to the, when we get close to this boundary. So you know that the temperature shrinks, so the intrinsic length of this vector should be very large. But with our stereographic projections, this vector gets mapped to vectors that are also quite small. Okay, like everything shrinks. So if we want to ensure that all those small Euclidean vectors get large Poincaré norms, we should always have like a temperature that goes to 0, and so distances that blow up. And around this location, it's exactly what happens. Because here, x gets close to 1, 1 minus x squared gets close to 0. But here, z is close to 0, and z on the blue space is also close to 0. So, I mean, it's all coherent. That's easy. And maybe the setting in which it's not that easy, it's at the other end of the spectrum. Because now, if I get close to this point, small vectors on the red space will also get mapped to small vectors on the green space. Okay, so that makes sense. Small vector, I should have a temperature that goes to 0 to have a Poincaré lengths that blow up. But on the blue space, a small vector is going to get mapped to a larger and larger vector. And so to a larger and larger Euclidean vector. It's exactly the same distortion phenomenon as what you had on Greenland, for the Mercator projection. And so to compensate for this, we have to have a temperature that does not shrink to 0, but that goes to infinity. And that's exactly what we get with this formula. With a temperature Z that goes close to 0 here, but that goes to infinity when I go up. Okay, and so those are the three main models of the Poincaré segment. But we can obviously do the same thing, a bit more involved, in 2D. So now instead of having a segment, we're going to have a disk, but we keep the same stereographic projections. So I just add a y coordinate. So here I have my Poincaré disk in 3D. Using the same stereographic projection, I map it onto a half sphere that I call J. And then using a stereographic projection from this point, I map the half sphere to the half plane, H. And now, well, you can trust me that we just added another coordinate Y. So for instance, points on the disk, before they had just one coordinate X, now they have two coordinates X and Y. Points on the half sphere, they had two coordinates, X and Z. Now they have three coordinates, X, Y, Z. And finally, on the half plane, we had just one coordinate, Z. Now we have two coordinates, Y and Z. Okay, so X, it's always going to be this direction. Y is always going to be this depth direction. And Z is always going to be the height. Z is always going to be height. And now, basically, those formulas, they worked in dimension 1, okay, with temperature 1 minus x squared, Z and Z. Well, it's the same story in 2D. So now we have 1 minus x squared plus y squared. On the half sphere, we have Z. And on the plane, we have Z. Okay, so those are formulas, like you can try to understand that. That's why it's going to be important to make a break. But okay, the only thing to remember, for instance, between the red between the red disk and the green hemisphere, you know that the temperature should go to 0 at the boundary. And the boundary of the disk is exactly the point such that x squared plus y squared goes to 1. The boundary of the hemisphere, that's exactly the point such that z goes to 0. Okay, and same story for the hyperplane. So those are formulas, and I think it's much easier to understand what happens if you display Tissot's indicatrix on the Poincaré disk, on the Poincaré hemisphere, and on the Poincaré half plane. And so whenever you see a formula for Riemannian metric, or you want to understand distortions, probably you can try to generate such a plot. Okay, so let's look, for instance, at the Poincaré disk. Okay, the metric was 2 times the Euclidean metric divided by the temperature. And so if I want to represent locally what does the metric look like, I should display at every point a disk with radius which is equal to the temperature. So here I represent at every point a scale unit ball. Okay, so here, so the radius is equal to 1. Here it's more like it should be 0.75. And as you get closer and closer, it gets smaller and smaller as you get closer and closer to the boundary. Now, same story on the hemisphere, but you can think of those things as just the images of the disks by the stereographic projections. So now the metric, it's like the normal Euclidean metric on the tangent space, on the tangent plane of the sphere, divided by z. So here I have a normal unit disk, and here I'm just displaying tangent disks with radii that are equal to z. And finally, here I do exactly the same thing. I'm just displaying disks on the half plane with radii that are equal to z. And so all those pictures, they are like in bijection with each other. Like these points correspond to this point that corresponds to this point using my stereographic projections. And so this picture, they just provide you different distorted lenses, so different photos of the same space. And now, when we see, at least this picture is the simplest one, I think, because it's not 3D, it's not curved, it looks very straight. You have a half plane, you have lines of equal coordinate z, and you just display balls you just display disk with radius z. And when you look at this discrete Poincaré grid, maybe you think that it looks a little bit like a tree, okay? Because every point, at every level, you have more neighbors downwards than you had neighbors upwards. And that's what motivated people to define a discrete Poincaré space that we call the discrete Poincaré grid, which is defined as follows. So initially, you just take a point, a node, that is enclosed in a square. So let's pick this one. And what we're going to decide is that on the horizontal line, you just replicate the same node. But whenever you go down, you add two neighbors. So you take the same, a bit like as in a fractal, you take the same cell, but you divide its scale by 2, and you get two neighbors. And then likewise, when you go up, you merge with one of your neighbors. Okay. And so this defines a graph. This procedure defines a graph where every point has exactly 5 neighbors. So one on the left, one on the right, one going up, and 2 going down. And if you do that, what happens is that if this is your coordinate z, your altitude, then the scale of your square, and so the scale of your ball, if you want, is exactly proportional to z. So in a sense, this is very much a discrete equivalent, a discrete analogy for this space. Okay? And this type of grid is funny, actually. It's something that you see if you study, especially signal processing. It's what we call an octave grid that is based on a dyadic tree. I don't know if you take the lecture about wavelets, but whenever you do wavelets, okay, you see those kind of grids popping up in a time frequency plane. So that's a nice continuous analogy. And so now I think we should make a break, because otherwise it's going to be impossible to follow. But what we're going to study now that we have defined essentially those 4 different models for the same space. So 3 continuous spaces and 1 discrete equivalent. We're going to try to understand what are the shortest path in this plane, and we're going to see that the shortest paths are not straight. Okay, so that's a general story. So now, the main target of this lecture is not to have you remember everything there is to know about the Poincaré disk, but just to let you be a little bit more confident of the fact that it's possible to define a metric locally and still get global results. Okay? And maybe the most iconic way of doing that is to show you that we have defined this Poincaré metric using a field of temperatures. We just using a formula. We are going to be able to find nice expressions for straight paths, okay, in this space. Okay, and then after that, I will tell you how we do in the general case. But that's why we spent a few hours doing equations and proving it. But even though I know that it's fairly hard to understand that on the fly using a Beamer PowerPoint presentation, this is a message that I want you to keep. Not really the expressions, not the expressions of the metric. This does not really matter. It's more about the spirit of going from local to global in one very well understood case. Okay, but first, let's start with the basics. So discrete objects. And okay, so we look back on our Poincaré grid. So this graph where every point has 5 neighbors. That has this kind of octave dyadic structure. And we're wondering about the look of shortest paths. So, okay, this is a source node, black node, and a target node, a white node. And okay, they are both at the same altitude. And like, what are the shortest paths? Okay, so maybe the most obvious short path is to go straight, using this red path. You make 1, 2, 3 jumps and you're there. Okay, so that's expected. But maybe what was not expected is that you can also go up and down. Okay, you can also go one way up, so you pay a price, but it's worth it because at higher altitude, you can go horizontally much faster. Okay, because the metric is dilated. That's really what it's about. So basically here, for those two nodes, both paths have length 3. So they are both geodesics in this discrete space. And now what happens if we go a step below? Okay, so now my source node is here, my target node is there. Now going horizontally, I would have to make 1, 2, 3, 4, 5, 6, 7 steps. Whereas if I go up, make 1 step right and go down, I only have to make 5 steps. Okay, so since 5 is smaller than 7, you say that, okay, this is more of a geodesic than this. Okay, and so that's something that we can immediately see on this discrete space, and we're going to show that it's also true with very nice expression for those circles, for those arcs in the continuous Poincaré space. Okay, so now we'll focus mostly on the Poincaré half plane because it's a space which is easier to display and which has the simplest metric structure. So let's say that we are on the Poincaré half plane and that I have a source point, a target point, that both lay along the vertical axis. So their coordinate y is equal to 0. It's the simplest case where, okay, this is my source, this is my target. And now I'm interested in finding a path that has minimal length between them. Well, maybe to do that, I should first take any path. So let's take this red path, okay, with coordinates y of t, z of t. So y, it's a horizontal axis, z is a vertical axis. And compute its length. So by definition, the length of y of t, z of t is the integral, okay, on the time interval, so here 0, 1, of the Euclidean norm of the velocity. So okay, so this notation with dots, it's what we do in physics whenever we want to indicate a time derivative. So y dot of t plus z dot of t squared, and you divide this by z of t. Okay, and this is your length. So in the general case, it's not easy to see how we could minimize this, like how, because if you want to go right or left, if you want to make a horizontal movement, it's not clear whether or not it's not clear if you should do your horizontal movement when you're on top or where you're down below. So maybe the situation is complex, but here, if this is my source node and if this is my target node, if they both have the same y coordinate, then I know that making any kind of displacements horizontally is useless. I don't need that in my path because just by properties of the sum of two positive numbers, the square root of y dot plus z dot is smaller than the square root of z dot t. So I just have this inequality. Oh no, sorry. The inequalities goes in the other no. Okay, so it's a typo. No, it goes in the other way. It's L excellent, not G excellent. Okay, so this term is always larger than this one, and this is exactly the formula for the length of a curve that is essentially the projection onto the vertical axis of the red curve. Okay, and so that's why you can say that at least the vertical axis of the horizon of the Poincaré half plane is a geodesic curve. Okay, because whenever you have 2 points on this line, the shortest path is just to go straight, just because of that, because of this inequality here. And now it's okay. We're not going very far, but we can use our stereographic projections, okay, because we have defined those bijections between our 3 spaces, you know, to ensure that they are just mirrors of one another. And so if I have a geodesic in the Poincaré half plane, then its projection onto the hemisphere and its projection onto the disk should also be geodesics. Okay, it just makes the definition of my matrix. And so what is a projection onto the sphere and onto the circle of this vertical axis that I'm displaying here? Well, to see that, you have to say that, okay, remember that the center of the hyperbolic half plane, so the point of coordinates y equal to 0, z equal to 2, is projected onto the north pole of my hemisphere and onto the center of the Poincaré disk. And then just by symmetry, you know, it sounds fair to say that this vertical axis gets mapped onto a kind of Greenwich meridian, you know, on the hemisphere. And it just gets rolled by the stereographic projection. And then when you project it back onto the Poincaré disk, you just get one of the diameters of the Poincaré disk. Okay, and so we know that just by using those changes of coordinates, we should be able to prove that just like this was a geodesic path, then this and this are also geodesic paths on their respective spaces. Okay, and now, okay, we have 2 other non-trivial geodesics. And what's interesting, what we can remark now is that the Poincaré metric, for instance, on the hemisphere was invariant to rotations. Okay, it's something that was kind of clear on this picture. Okay, if you rotate this hemisphere, or if you rotate this disk, you do not change the distances, you know, because the metric here, so the term here, it's just a Euclidean metric, so it's invariant by rotations in 3D space. And the temperature Z is also left constant by those kind of rotations along the vertical axis. So if you want to show it like at a calculus level, you would write down that a rotation of angle theta, you know, along the vertical axis is a function that takes x, y, z, and associates cos theta x, sinus theta y, and z, and that basically, so they do not change z. And if you look at what happens to the dx, dy, dz square, so dz square doesn't change, and dx square plus dy square, you get cos square theta plus sin square theta, it's equal to 1, and so it collapses. And so, okay, so this is the way you understand that this metric is invariant to rotations. And so since my Greenwich meridian was a geodesic, then all meridians should be geodesics. So notably, among others, the meridian that cuts the Greenwich meridian at exactly 90 degrees is also geodesics. And then we can project it back onto the Poincaré half plane. And so if you look at the projection of this half circle onto the Poincaré half plane, then it's also going to be a half circle, you know, just by Thales theorem. So now, you know, just using this clever projection, rotation, projection back, we have gone from having one geodesic to having 2 geodesics. And actually, we could do that with any rotation angle, and it would give us loads of geodesics on the hemisphere, loads of geodesics on the disk, and lots of geodesics on the half plane. Okay, and so this is what I display to you here. So just by the invariance of the metric to rotations, you can show that all the diameters of the Poincaré disk are geodesics, and all the meridians of the Poincaré half plane of the Poincaré hemisphere are geodesics. And now the images of those half circles by stereographic projections are also half circles. So that's typical triangle geometry, you know, from the Greek era. And so we can show that all the half circles that pass through this point, you know, which is the image of the North Pole, are geodesics in the Poincaré half plane. You know, and that's already quite nice because here you see the exact same phenomenon as what we had observed on graphs. Okay, if you want to go from this place, from this source point to this target, then it's not worth it to try to travel, you know, travel on foot by horizontally. You'd better go up, travel fast, and then go down. A bit like taking the plane. And obviously, the metric is designed in such a way that everything looks super smooth with circles of arcs and everything. But that's really the spirit. So now, so a priori, the only half circles that are geodesics are the ones that pass through the North Pole, so through this point 0 plus 2. But then we can look again at this metric, at this Poincaré metric on the half plane, which is the Euclidean metric divided by z. And we remark first that it's invariant by two horizontal translations. You know, if I change the y coordinates, the horizontal coordinates of my points, so to yz I associate y plus delta y and z. You know, here I do not change the differential terms, I do not change the z, and so I get the same length elements. Okay, so it's also something that's clear when you look at Tissot's indicatrix. It's invariant by translation, and so you know that all the horizontal translations of those half circles are geodesics. Actually, this already gives you all the half circles that are orthogonal to the boundary of the domain. Okay, so that's one thing. Another thing that we can remark is that the metric is also invariant through scaling by the positive constant a. Okay, it's also something that you can see on the Tissot's indicatrix. You know, if you scale everything by a factor of 2, you recover exactly the same Tissot's indicatrices, just because everything has been designed this way. And if you look at the formulas, if I multiply the velocity by a, I also multiply the altitude z by a, you know, the term collapse, and so I recover the same metric. Okay, and so this allows me to show that all the half circles that are perpendicular to that are normal to the boundary are geodesics. And now, using just those curves, I'm able to join any 2 points on the Poincaré half plane. Because if this is my source point, if this is my target, using simple geometry, you can show you take a compass, or you take a bisectrist, all of that, you're able to find the center of a circle on the boundary, such that this half circle joins your 2 points. And so we have fully described the geodesics on the half plane. Then using projections, you can project them back on the Poincaré disk. And now we are done with our description of the Poincaré disk, you know, at first level. So on the Poincaré grid, geodesic paths are like those up and down trajectories. On the Poincaré half plane, you have vertical lines and half circles. And on the Poincaré disk, you have diameters and arcs of circles that are orthogonal to the boundary of the disk. Okay, so kind of nice discrete to continuum equivalence. Yes.
But similarly to the octave tree, did it happen for the Poincaré sphere that we have two geodesic? It is two paths that are of minimal length from the points.
No. Okay, so this you can show there. You know, essentially, just like here, okay, it comes down to the fact that between those 2 points, you only have one path with minimum length up to reparametrization. And because of that, because of this unicity between those 2 points, you can show, you know, using all those symmetries of the space, you can show that it's going to hold for any 2 points in the space. So you really have just straight paths between any two points. Okay, so, and that's kind of a famous result. That, you know, has been used quite a bit heavily in some art. So maybe you've already seen this picture by Escher, pretty famous one, like circle limit 4, like a bit like angels and demons, where you have a tiling of a disk that looks like a fractal pattern, but for the Poincaré disk, you know, for the intrinsic metric of the Poincaré disk, this is a uniform, a regular tiling. Okay, and you see that the number of nodes, you know, grows exponentially with the distance to the center. You know, another thing that I showed you, I think it was 2 or 3 lectures ago, is this graph. You know, and I told you that this is a kind of nearly a tree. And actually, this graph is what we call the Cayley graph of a group of matrices, SL2 of Z. So the 2 by 2 matrices with integer coefficients that are also invertible. And these act as isometries. So these are isometries on the Poincaré half plane, just like translation by integer coefficients are isometries of the Euclidean plane. And so if you want to represent the group of integer translations on the Euclidean plane, you would use a grid, because this is a group that we call a Z Cartesian product Z, so Z squared. It's a grid. Here, it's kind of the equivalent for the Poincaré space. Okay, and you see that it looks like a tree. Okay, and this is where all of this literature on curvature and all that comes from. So now, just a recap on the Poincaré disk. Okay, I don't want you to remember, you know, this stuff about like the precise form of the stereographic projections has zero impact on your work in data science. But the method, I think, is very important. Okay, so you should remember first that a Riemannian metric, it's given to you in textbooks as a smooth field of Euclidean norms. But if you want to understand it graphically, it's really equivalent to Tissot's indicatrix in cartography. So it's something that makes sense. And, you know, isometries, you can see that they are isometries because they preserve this field of indicatrices. Then, okay, the reason why it's so popular is that it's the Riemannian framework is so popular is that using simple tools from calculus, using simple square dot products, symmetric matrices and integrals, we're able to define arbitrary geometries. Okay, just using a field of temperature, people have been able to define a disk which behaves like a continuous tree. So it's very good trade-off in terms of mathematical complexity against the expressivity of in terms of geometry. It's really appealing. And maybe, you know, with respect to proof, you know, I could have shown you proof of the structure of geodesics of the Poincaré disk that rely purely on computations. You know, it's a standard proof. It's just to derive things. You know, you have matrices, blah blah blah. But I don't think you understand much. Okay, when you look at these proofs, and here you see that I was able to show you a pretty elegant proof that comes from this paper from the 90s because I used those change of coordinates. And so maybe it's a message for you. If you do a PhD, you want to prove theorems, usually changes of coordinates are key to the eloquent proofs, and you don't want to get too stuck on one parametrization. You know, exactly when I told you that if I have a mesh, if I have a surface, a human body surface, maybe I want to understand it as a point cloud, maybe I want to understand it as a mesh. You know, it's the same spirit in mathematics. You have an object and you have different ways of describing it, different equations for the same objects. If you're able to jump from one description to another, you're able to be much more productive. Okay. And finally, the fact that those discrete continuous analogies, they go both ways. We understand tree-like graphs much better now that we have this hyperbolic understanding, and vice versa. Okay, I think that having this discrete intuition for what happens in a Poincaré space, I think was helpful to understand that this is not that this is grounded and that those half-circle geodesics make sense. So that's the spirit in which mathematicians work today. Now, okay, that was a toy example, but how is all of that relevant to data science in practice? Okay, so first, Riemannian geometry, distorting the metric on a surface, on a disk or on a plane is a very convenient way of working with surfaces. Okay, just imagine that you want to work with a donut, with a torus. If you look at math or computer graphics paper, you will have two main ways of representing such an object. The first one is to understand your torus as a 2D surface, which is embedded in 3D. And that's kind of good. Like it's good for rendering, definitely, and you can this point of view allows you to express the fact, for instance, that this inner circle, this magenta circle, is much smaller than the red circle. Like you have everything you want. But if you want to work on the torus, this description can be very cumbersome. Okay, because imagine that you want, for instance, to make optimization, you want to find the point on the torus that minimizes a given quantity, and you want to perform gradient descent. You want to perform gradient descent with a point that has to stay on the torus. Then if your only description of the torus is that it's a 3D object, it's a 2D object embedded in 3D, you will have to do projected gradient descent. You will have to have XYZ coordinates for your points, make small gradient steps, and then at every step project back onto the torus. If you want to compute geodesic trajectories, kind of same story. So the fact that you have extra degrees of freedom means that you have to project back at every iteration. And so it's less than ideal from a computational or theoretical perspective. So maybe what you can do instead is to describe your torus as a flat 2D square, where you have identified this side of the square, so the top side of the square with the bottom, and the left with the right. Okay, so here it kind of makes sense. So this blue path corresponds to this blue circle. The red path corresponds to the equator. And here I have identified this with this. Okay, so maybe if you have played like old school video games, like on Game Boy, typically the worlds in video games look like this in standard Japanese role-playing games, like in Pokemon or in Final Fantasy. You had those maps where if you went up to the top, you appeared back in the South Pole. Okay. And that's the structure that you get. But okay, it's convenient, definitely. Basically, to work in this space, you just have to be able, essentially, to compute integer parts. But out of the box, it doesn't really allow you to express exactly the same geometry as here. Because out of the box, if you work with a flat 2D square, then this equator has the same length as this equator. So out of the box, you feel that you have to make a decision. Either you work with the actual geometry you're interested in, but then you have too many coordinates, or you work with exactly the correct number of parameters, but you do not get to choose your geometry. And obviously, okay, the answer of Riemannian geometry is to say, no. We are going to distort the metric. We are going to say that here, especially along the horizontal axis, the distances are shorter, whereas here they are longer. Okay, and so just defining a field of Tissot's indicatrices, or equivalently a Riemannian metric on this 2D square, allows you to distort this geometry by hand. And then, if you work in this 2D space with a curved geometry, it is provided to you by those Riemannian metrics, you are able to compute geodesics. Okay, we call that shooting equations. I'm going to show them to you quickly after. So purely in 2D space, so with very simple closed form equations. And then when I project those trajectories onto my 3D space, onto my 3D surface, they really look like 3D geodesics, even though they were computed purely in a curved 2D space. So that's the first motivation for studying Riemannian geometry, is that it's a framework that allows you to work with a proper number of parameters without compromising on the actual geometry that you're interested in. So for everything related to graphics, it's very popular. Now, that's one thing, that maybe unlike me, you're not really interested in 3D. You're more interested in like covariance matrices, rotations, I don't know. And all those types of mathematical objects do not really live in vector spaces, right? For instance, if you look at covariance matrices, they live in a cone of a positive definite matrices, so not really a vector space. And so here, I'm displaying to you one covariance matrix in 3D, so an ellipsoid. You can think of it as PCA, but for a point cloud, which is very horizontal. And here a second covariance matrices for like another PCA for another point cloud. So here I have two ellipsoids, two 3x3 symmetric positive definite matrices. And I'm interested in interpolating between the two. So between those two 3x3 matrices objects. And so the naive way of interpolating between covariance matrices is just say these are matrices. I can interpolate coefficient-wise. I just have arrays of data, and I interpolate using linear interpolation for the coefficients. So you can do that, and from a geometric perspective, this is equivalent to saying that the cone of positive symmetric definite matrices is embedded in a vector space of matrices and just go in a straight line. So you can do that. It's kind of the Euclidean metric on covariance matrices. But if you do that, this is a type of trajectory that you obtain. And notably, so it looks a bit strange because here you had two very thin covariance matrices, and instead of getting a smooth rotations, you're getting a blob in between. You can make it, you can quantify this by just displaying along the trajectory the volume of your ellipsoid. So it's like the determinant of the square root of the covariance matrix, and you see that it makes a bump in between. And so in many applications, it's not really what you want. It's a bit trendy. It looks like a strange bias that is introduced by your interpolation routine towards roundish shapes. And so instead, what people do in all applications where this kind of artifacts is undesirable is that we understand the cone of covariance matrices as a Riemannian as a space endowed with a Riemannian metric. So typically we use a affine invariant or the log Euclidean metrics, and then using the geodesics for this metric, we're able to interpolate in a much smoother way. Okay, so things like this and this. Okay, and so for instance, these images they come from a paper by Xavier Pennec, who makes a lecture on medical imaging in the MVA. And this is actually super motivated by applications to a diffusion MRI. So what happens with an MRI is that you can observe at every voxel location in your body, you can observe how water diffuses. And so, for instance, those kind of very anisotropic covariance matrices appear whenever you observe an image in a tissue where you have fibers. So typically it's in the brain or in the bone marrow, not in the bone marrow, but in the spinal cord. Basically, you have those wires of white matter that defines a very strong anisotropic structure. And so you observe at every location an ellipsoid that tells you that, okay, the wires go this way or this way. And the thing is that as all medical images, out of the box, these are super noisy. So you want to denoise them. So to denoise, you want to compute local averages. And the problem is that if you were computing local averages using this naive Euclidean formula, we would blur everything. And we would lose this directional information. Whereas now, I mean, we've known now for 15 years that it's possible to do denoising, but like in this manifold space, and retrieve much better behavior. Okay, and so that's for 3x3 covariance matrices, but you can definitely apply this to large covariance matrices. Like it's interesting to understand it as a Riemannian metric instead of a Euclidean curve. Another setting is very typical in computer vision or in robotics is that you want to deal with 3D rotations. And once again, 3D rotations, you can think of them as matrices. But if you have one 3D rotation matrix and a second 3D rotation matrix, if you add them together and divide by 2, you do not recover a 3D rotation matrix. So if you want to make interesting interpolations and all that, it's strongly advised to try to use the intrinsic structure, typically a Lie group structure or a Riemannian metric on those fields. So that's what is represented here in a rotation between one 3D frame and a second. Now, another field of applications, still remaining in the realm of mathematics, is probability distributions. Okay, and this we're going to make a whole lecture about it next time. So a bit of a spoiler alert, but maybe the most vanilla probability distributions that you can imagine, that's the Gaussian distributions on the one-dimensional real line. Okay, so probability distributions that are completely described by their mean value and their standard deviation. So now you have a kind of two-dimensional family of probability distributions. And it's interesting to wonder, like, what happens if I put a geometry on this? Like, how can I compute distances between those probability distributions? And it's something that you do all the time, especially if you do deep learning, because every time you do classification, at the end, what you do is you predict scores. So you predict probability distribution of belonging to one class or another, and then to compute your loss function, so to compute something to optimize. Typically, you optimize a distance or pseudo distance between your predicted probability distributions and the ground truth distribution, which is usually a direct mass. And to do this, usually you use like a cross entropy or something like that. Like there are many different loss functions or distances between probability distributions that are implemented by PyTorch. And the interesting thing is that those distances induce very different geometries on the space of Gaussian distributions. So for instance, we're going to see that if you use a Wasserstein metric that comes from optimal transport theory, so there's a whole lecture on that, then what you are really doing is that you are endowing the space of parameters, mean, standard deviation, with a Euclidean metric. So for instance, the geodesic, so the shortest path for the Wasserstein metric between two Gaussian distributions is just a straight path, like you interpolate linearly between for the mean and the standard deviations. So that's one thing. But another thing very popular is to use something with an entropy in the name, like a relative entropy. And the thing is that if you compute local distances between Gaussian distributions using a relative entropy, then what you are really doing is that you are endowing the space of Gaussian distributions with a Poincaré metric. Okay, and that was also one of the reasons why I spent so much time on the Poincaré half plane, because it's exactly the structure that appears when you consider Gaussian distributions and you use a cross entropy. So, and just, okay, we're going to spend time on this, but what is the intuition behind what happens here? So you imagine here I have a point, so a distribution which is very peaky, so small standard deviation and mean to the left. And then I have another Gaussian distribution, which is quite peaky and a mean to the right. Okay, and so the optimal transport geodesic, so the Euclidean geodesic, just say, okay, if I observe at time 0, I observe this geodesic, I observe this Gaussian distribution, and at time 1, I observe this other Gaussian distribution, then I can assume that the mean and the standard deviation just evolve linearly. Whereas with my entropy formulas, I assume that first, the standard deviation increased a lot, so confidence collapsed. Then we moved a little bit, and then confidence started to grow again. Okay, this kind of geodesic. And the thing is that it's not absurd to prefer this kind of behavior over this one. Maybe an example, it's a bit tongue-in-cheek, but imagine that the real line here, it's like political opinions. And that basically here you see someone age 20 with super left-wing, super confidence on like one party. You observe him at 60 and also quite confident, but like with right-wing conservative views. what is the most likely trajectory? Like, was he confidently socialist, confidently centrist, and then confidently right-wing? Or did he kind of have an in-between phase where he didn't really know what he preferred, and then he went back to another opinion? So obviously for politics, I don't know how it works, but you can imagine that in many settings, if you want to follow customer preferences and all that, you would prefer this kind of behavior. Okay, and that's one of the most ubiquitous use of hyperbolic geometry, so Poincaré geometry in machine learning. So another example where Riemannian metrics appear kind of naturally is whenever we deal with shapes. Okay? And if you remember lecture 1, I talked to you about triangle shapes. We saw that you could represent them on a plane, but that it was much, much, much more elegant to represent them on a sphere of radius 1/2. Okay, and so this is an idea from the 70s and 50 years ago, and now people have worked more and more on this. And now whenever we do anatomy, so whenever we deal with shapes of hands, of human surfaces, or organs, we really prefer to see them as points in a curved space that has nice structure. And why is that so? That's because if you're able to define a nice metric on your space of shapes, then your geodesics are going to look good. And so you're going to be able to understand natural plausible evolutions, not as strange, nonlinear evolutions of point coordinates, but as nice, smooth, straight trajectories of the shape in a curved space of shape. Okay, so those are figures that I showed you in lecture 1. So maybe we can take the hands here, the skeleton hands. So to produce those figures, what the authors did is that they say, okay, a hand, you can say it's a point cloud. Okay, point cloud, a big vector. So my domain, instead of being a Poincaré disk, is going to be a high-dimensional vector space. And I'm going to define a metric. So to define a Riemannian metric, you just need to define a quadratic formula that penalizes small perturbations, small deviations. You just need to say, what is the distance locally between this hand shape and another positions of the vertices? And to define this quadratic formula, okay, the authors here, they use a kind of, basically they open a textbook of mechanical engineering. They assume that their shape was made out of an elastic material, homogeneous elastic material, and then just computed the kind of energy, the deformation energy between one state and another. And when you use this kind of formula, you're going to accept isometric deformations of the shape, but you're going to penalize very heavily tears, like strong distortions. Okay? And this kind of model, you can totally understand it as a strange Riemannian metric on a space of point clouds. And once you have this Riemannian metric, using mathematical tools, you're able to trace geodesics. And so you're able to interpolate between two positions and even extrapolate with some degree of confidence. Okay, which is something that you really could not have done without this curved space, or it would have been hard. Because, for instance, if you look at the tips of the finger, okay, so here the tip is here, here's the tip is there, time 0, time 1. Then if I had used like a linear interpolation, it would have been completely unrealistic with the tip of the finger somewhere around here. Whereas here, because I used linear interpolation in a curved space, I was able to retrieve a curved trajectory for any points. So, okay, you can compute geodesics and you can compute barycenters. And if you're interested, you can just look at the references. We can do a lot of things now. So that's for mathematical or 3D objects. And finally, I think another field or another area in which Riemannian geometry pops up is actually whenever you train a neural network. Okay. And why? That's because you can understand those network architectures that we work with as projections from a space of parameter, like from your space of neural weights, to a space of function, to a space of estimators. Okay, so we saw an hour ago, we saw that Riemannian geometry appears, like Tissot's indicatrices appear every time you consider a projection between two metric spaces. So we saw that, for instance, what we do in cartography is that we assume that the Euclidean metric on the sphere is good, is meaningful. Then we project this space onto another, like onto a sheet of paper. And then we understand the real metric on the map as a Riemannian metric given by Tissot's indicatrix. And if you think about it, it's really what we do in deep learning, because, okay, you have your space of parameters, neural weights, and using your architecture, like all your ReLU, all your convolutions, you define a function out of it. And the whole game of deep learning is to try to find good parameter values such that the function that they define, so your trained neural networks, fits well the data set. So from a, from an outside perspective, what we're really trying to do is to find a function in the family of convolutional neural networks that fits the data well. So we are more interested in what happens in the space of estimators. Like, we never compute errors in the space of parameters. We always evaluate our estimators as functions. So we are very much interested in what does my function look like? How does it compare against other estimators? This kind of thing. But instead of performing gradient descent in the space of estimators, we never perform gradient descent in a space of functions, or very rarely, and deep learning never. What we do is we perform gradient descent on parameters. And the thing is that maybe you've seen that in some of your lectures. I don't have time to delve into it, but whenever you do gradient descent on some variables, on some parameters, you are really making gradient descent for the Euclidean metric on those parameters. And so you assume that the Euclidean metric makes sense on your space of parameters. And so the whole procedure of training of a deep neural network is define a projection between a space of parameters to a space of interesting functions, perform standard gradient descent on the space of parameters. And this is actually kind of equivalent to making Riemannian gradient descent on the network. And so if you want to understand how does the estimator evolve with your iteration number, you have to have these Riemannian ideas in the back of your mind, because we are not really interested in how the parameters evolve. We're interested more into how does your trained neural network progressively gets closer and closer to an optimal estimator. And so those ideas, they are really, most of the time explicitly, but always implicitly, behind all the papers that you can read on natural gradients, neural tangent kernels, or Wasserstein gradient flows. That are all of those tools useful to try to understand why a non-convex optimization procedure, like stochastic gradient descent on neural networks, in practice tends to converge towards good local minima. Okay, so the whole theoretical literature, at least, is very infused by those ideas. So that's the thing. And finally, maybe more related to what we saw last week. Well, we saw that the Poincaré disk is somehow a tree. Well, it's very easy to embed trees in a Poincaré disk. Okay, so that's you have combinatorial algorithms to do it. And maybe if you want to look at more real-life data sets, here it's an embedding of the set of all names of mammals into a Poincaré disk. And this allows the specific geometric structure of the Poincaré metric allows us to embed like mammals, ungulates, carnivores, rodents, into this space without having too many crossings between the edges. Okay, so that's one thing. Another thing is that I presented to you UMAP, and if you look not just at the algorithm UMAP, but you look at the paper in which it was described, you can see that it's called UMAP because it's uniform manifold approximation and projections. So the whole paper was infused by Riemannian ideas. And just to be clear, manifold it just means, as I told you, it just means surface. So, and why don't we just talk about surfaces? It's because, you know, with the Poincaré disk, it was easy because I could describe all the points of the Poincaré disk using a single domain of the Euclidean plane. But maybe if you look at the sphere, for instance, or the torus, you cannot really define a bijection between a domain of R2 and a sphere, because you're going to have problems whenever you have foldings. And so what mathematicians do when you deal with those surfaces that have a more complex topologies is that we define a collection of patches and we patch them together explicitly, okay? And manifold, it just refers to this collection of patches. So, okay. Basically, Riemannian metric, you can define it on a single domain or on a collection of domains, and so on general manifolds. Yeah, that's where the name comes from. So, just good thing, and maybe, okay, just to finish on that, you know, it's important to understand how we work, how we are even able to work with all those strange Riemannian metrics, because I showed you that, okay, in different domains, whenever you deal with surfaces, tensors, probability distributions, shapes, or neural networks, somewhere we define a Riemannian metric. But how are we able to compute geodesics in the general case? Well, okay, we saw that in the best case scenario, like the Poincaré disk, we're able to, using some mathematical proofs, to find closed form expressions for the geodesics. But for general Riemannian metrics, you cannot hope that this will be true. Okay, you cannot hope to have explicit formulas for geodesics on an arbitrary human body surface. What you can hope for instead is to hope for a simple mathematical structure. And this is given to us by strong theorems that are called the geodesic equation, especially in what we call in Hamiltonian form. So what do I mean here? And this is going to be by far the last complex slide of the whole class. Okay, so we've seen that the Riemannian metric is given at every point Q, or every point X, by an n by n matrix, a metric, positive definite matrix. And so what we define is a function that is called a Hamiltonian that takes as input a point and a velocity vector, or what we call a momentum vector, and compute the square norm of this momentum vector using not the metric, but the inverse of the metric. Okay, because your metric locally, it's a symmetric positive definite matrix, so it's invertible. You have positive eigenvalues, so you can invert these. You get another object that is called the cometric, and you use that as a kind of dual squared Euclidean norm. Okay, that's called the Hamiltonian. And then you have very strong theorem about structure, where we can show that path is Q of t that minimize lengths, at least locally, because you cannot hope to minimize lengths globally. Like if you look at geodesics and the sphere, you know, they end up looping around. So it's a bit strange, but so if you look at paths that minimize lengths locally and travel at constant speed, then we can show that they necessarily follow a coupled ordinary differential equation of order 1. So where you couple the position with a momentum vector P of t. So at every point Q of t, you also have a momentum vector. And the equations look like this. So the velocity, the evolution of the position Q of t, so dot of Q of t, is given by just the partial differential of the Hamiltonian with respect to P at your current state in phase space. So at current position Q of t and momentum P of t, you compute this partial differential and gives you the velocity that you should follow. So this formula just tells you that given your current position and your current momentum, you have a unique formula to compute the velocity. And then the most interesting formula is this one, that we also have an explicit equation that tells us how the momentum vector should evolve. And that's that the time differential of P should be equal to minus the partial differential of the Hamiltonian with respect to the position at current state. And this equation tells you that you should steer the momentum, just like a driving wheel, following this equation if you want to stay on a geodesic path. So this is a very nice result, and if you look at in the references that I gave you at the start of the lecture, you can find proof, sketches of proof. You can really understand that it's very important in physics and in geometry to understand where those equations come from. But at a high level, you do not really need to understand what is this Hamiltonian and where do the partial derivatives come from. The only thing you need to really keep in mind is that the evolution of your position is entirely is given by this ordinary differential equation. And you know that an ordinary differential equation of order 1, where you just have the time derivative, is completely determined by your initial state. Okay? Because if you have such a differential equation and initial values for the position at time 0 and the momentum at time 0, then using some kind of Euler integration scheme, you're able to reconstruct the trajectory at all times. Okay, that's what in the US they call the Picard-Lindelöf theorem. In France, we call that the Cauchy-Lipschitz theorem. Okay, maybe you've heard about that. And so, what do you need to fully specify a state at time 0? Well, you need a position at time 0, and you need a vector of momentum at time 0. And you can show that getting this vector of momentum at time 0 is equivalent to giving the velocity at time 0. And so, thanks to those structural theorems, we can show that geodesics, like geodesic paths, are fully described by initial position and initial velocity. And basically, if I give you a path, I tell you it's a geodesic, it starts here in this direction, you're able to trace it fully. And so using that, we can define what we call the exponential map. Basically, the map that is defined at every point of your space and takes as input the initial momentum or the initial velocity, traces a geodesic until time 1, and stops where you arrive. So, okay, maybe I can look at this simple example, the one-dimensional circle, the unit circle, and look at this privileged position, which is a point q equal to 1. So this is a 1D manifold, and its tangent, basically the space of possible velocity vectors at time t equal 1, is just a straight line. Because you can go either no speed, slowly in this direction, fast in this direction, or you can go slowly in the other direction, fast in this direction. So we say that this line is the tangent space of the circle at this location. And then you say, what happens if I if I follow a geodesic? So a geodesic along the circle is just you go straight along the circle with initial speed which is equal to t, and I stop at time 1. Then since I know that geodesics travel at constant speed, I know that I will describe a circle of arc of length t. Okay, and so that's why the exponential map, so and that's where the name comes from. So the map that associates to every initial velocity a point on the manifold has exactly the expression exponential of it. Okay, because the complex exponential is defined by rolling a line along the circle. And you see that you can apply this methodology to any kind of manifold, actually, to any kind of Riemannian space. For instance, if you take the sphere, and as privileged point, you take the North Pole. Then you define your exponential map by saying, okay, the exponential map of this velocity vector is what happens if I travel at constant speed in this direction and I stop after 1 day. And if you do that, you get a point, okay? And it allows you to define a bijection between a local, like unit disk, at least for small velocity values, and a local neighborhood of your points. For instance, okay, this is what it looks like on the Earth. That's what cartographers call the azimuthal equidistance projection. It's here every point on the disk. Okay, so the disk has a radius of like 20,000 kilometers by definition. And every point on the disk is associated to a point on Earth. And it's made in such a way that at least radial arcs in this exponential map correspond to meridians, and so they correspond to geodesics. So you cannot expect that non-radial arcs also correspond to geodesics, because the Earth is not a flat space. But at least this kind of map, allows you to get a canonical vector representation of points on the space that are close to the North Pole. Okay, and so it's a tool that we really tend to define whenever we work with Riemannian manifolds. So the formal definition is that the exponential at point q0 of the momentum or velocity vector p0 defines a solution at time 1 of this geodesic equation with initial condition at time 0, you are at location q0, and you start with momentum p0. Okay, so it allows you to vectorize, here, the complex exponential allows us to vectorize the circle onto a line. And usually we like to work with vectors, even though we try to avoid that. So, and that's why, once you've gotten all of this background, you understand that in the general case, if you have a Riemannian metric and you just want to compute a geodesic or a distance between a source point A and a target point B, you have 3 main scenarios. The first one is that your metric has a lot of structure, like an affine invariant metric on a space of covariance matrices. Just the title looks mathematical. And when you're in this very favorable setting, then you can make proof, and you're going to find closed formulas for your geodesics. So just like the Poincaré disk, usually those proofs, you first show for simple examples that geodesics look a certain way, and then using symmetries of the space, you're able to extend that to all pairs of points. And so in practice, here in this setting, defining a Riemannian metric is just a way of ending up on a good kernel formula that you can use, to do interpolation or whatever. So that's for mathematical examples. But now, what happens if your metric comes from a physical description or comes from a neural network architecture and something strange? Then you have 2 major ways of computing your geodesics. The first one is maybe your metric has a simple structure, like it's easy to implement. And typically, this was the case with those elastic models, okay? Because the metric that pop up when you define an elastic model, they have a nice finite element expression. You can implement them using sparse matrices, so you have programs to evaluate this metric. And then, well, the thing you can do is just to find a path that minimizes lengths, you can just discretize a path and try to minimize explicitly a discrete analogous of the length, of the square length. So what you do is you start with your starting position, your end position, and you distribute, maybe using linear interpolation with your point coordinate, something very basic. You distribute snapshots, n snapshots, or n+1 snapshots between time 0 and time n. So they kind of correspond to times 1 over n, 2 over n, 3 over n, n-1 over n. And then you can say that the squared the squared Riemannian length of your geodesics, you can approximate the integral by a Riemann sum. You can approximate the velocities by differences between the positions of the snapshots. And then you know that finding a geodesic curve is like minimizing this, but where you compute the distances between 2 consecutive snapshots using the Riemannian metric at location, at current location in a shape space or whatever. And now, so you have this, and you try to minimize with respect to the positions of your snapshots. And this defines to you, if you do gradient descent on this energy with respect to the snapshot positions, you end up with a kind of mean curvature flow. And in favorable cases, you can implement it pretty quickly. So the main downside of this approach is that you tend to have a big memory footprint because you had one sample and you had to make n copies of that. So if your metric or if your space is large, maybe it's not tractable. But it's very simple, and at least for shape geodesics, for some types of metric, definitely this is what people do. Finally, the last favorable case is that maybe your metric is not simple, but the inverse of the metric is simple. And this is also something that happens pretty frequently. And then in this case, you know that you're going to be able to implement the Hamiltonian easily because the Hamiltonian, it's just a dot product with the inverse of the metric. So if you have a nice formula for GQ minus 1, you have a super nice formula for H of QP. And then if you have implemented using PyTorch your Hamiltonian, then using automatic differentiation, you're able to compute those partial derivatives. And once again, using PyTorch, you're able to compute partial derivatives. You're able to integrate the ODE. So you implement like an Euler scheme. And so you're able to implement the exponential. Okay, and this is much easier now that we have PyTorch because when I started working in this field like in 2016, before automatic differentiation libraries were mature, every time people defined a metric, they defined a Hamiltonian, and then by hand you had to compute the derivatives and even the derivatives of order 2. So it was very cumbersome. But now with the modern libraries that we have, it's very easy to implement. Basically, it's easy to implement this ODE, and so to implement the Riemannian exponential. And now, if you want to find a geodesic that goes from A to B, then you can just recast this as a problem of finding a good initial velocity, such that once you apply the exponential, you end up at the desired location B. And so it's an inverse problem that usually you solve either using an optimizer, or you train a neural network to predict given B, this is a P0. So this is what we call a Riemannian log, and especially in shape analysis, training a neural network to do this for you is usually tractable, a pragmatic approach. So that's the conclusion, for this very mathematical lecture. But I want you to remember 3 things. So the first is that, Riemannian metrics, okay, if the first time you ever saw this word was 3 hours ago, maybe you're still a bit under shock. But at the end of the day, it's just defining locally a field of temperatures. It's not that hard. And what's remarkable is that with this simple vocabulary, we're able to describe so many different geometric structures, like trees, balls, shapes, probability distributions. So we're going to see this stuff about probability distributions next time. The second is that since it's such a simple mathematical object, since a Riemannian metric is such a simple mathematical object, there is now a complete toolbox to work with that. So we completely know how to go from a local metric expression to a fully fledged geometric toolbox. Like we know how to compute geodesics, we know how to compute exponentials, we know how to compute barycenters. So, it's possible to start to do interesting statistics in arbitrary geometric spaces. And maybe, the ethos of this whole field, the appealing message is that, if you're given lots of trajectories, lots in a space, so it can be lots of shape interpolation, for instance. It's typical in neuroanatomy that we take snapshots of the shapes of the brain of people at age 70, 73, 76, 80, and unfortunately for some of them, we see that like the hippocampi are shrinking, okay, because they have Alzheimer's disease or something like that. So longitudinal data, it's very common, be it in shape analysis or in many other fields. Like you can also track drug consumption, these kind of things. And basically we have all those trajectories and we have to make a choice. Either we think that we are in a simple Euclidean space, like a Euclidean space of images, but then the trajectories don't make sense. Like, if you look at images as Euclidean vectors, maybe, and you perform a Euclidean PCA between all your brain images, and then in PCA space, you try to track evolutions, you're going to see strange zigzags. Nothing is going to make sense. And basically, you can try to work with complex passes on a flat space, but it quickly gets very hairy. Whereas maybe what you can try to do instead is you try to find a nice geometric structure on your space of images or on your space of data, such that all plausible trajectories can be explained as geodesics or near geodesics up to some noise. And this is a much more appealing model. First, because it looks nice, so it allows us to draw diagrams, to talk about trends, etc. But also because it allows us to aggregate information between different trajectories. So if you say that your space is fixed and you're trying to fit a very complex model for each individual trajectory, maybe it's complicated. But if instead you say, how can I distort my space with a Riemannian metric so that all my trajectories are kind of geodesic trajectories, kind of geodesic lines, then you have defined a way of aggregating information between different samples to construct a unified representation of your space of data. And so you try to extract meaning. Okay. So this message is a bit like a dream, but first, it's a cornerstone of several applied fields. So as I told you, in anatomy, it's completely ubiquitous, or in statistics, if you want to understand what happens with probability distributions, we really think of probability distributions as points in a Riemannian metric. And beyond that, I think that this whole spirit, it has consistently produced inspiring outlooks in many other settings. For instance, if you look at UMAP, probably people could have found the UMAP formulas, the UMAP algorithms without having all of this theoretical background. But as a matter of fact, they had this theoretical background, and they had this dream of trying to change the Riemannian metric of the space such that the data distribution is uniform, those kind of things. And those theoretical ideas motivated them to go all the way through. And I think maybe it's a message about the lectures that you find in the MVA. Some of them are very theoretical. I think you cannot always expect them to have direct implementations as algorithms. Most of the time, like if you look at convex optimizers, I don't know, Monte Carlo samplers, usually those methods, they have a niche field in which they are state-of-the-art. Just like Riemannian geometry, it's completely state-of-the-art for tensors, probability distribution, shapes. But it's still worth learning about them if you don't intend to work in those fields, because historically, they have really allowed people to be more creative with strange data sets and strange data structures. Okay, and that's why I wanted to spend like 3 hours explaining to you all of this and try to demystify this continuous vocabulary, because this is the vocabulary in which Wikipedia is written, and it would be a shame if you could not, if you close the windows as soon as you saw a derivative. So I hope that, okay, here you had to follow the lecture. Now we've done it, and hopefully you're able to understand what you read in textbooks a little bit better. And so now I think we only have 20 minutes left, so not a real lab session, but if you're interested in all of these Riemannian geometry things, I advise you to have a look at this GeomStats library and the tutorials, because it's a library that exactly follows this program. Essentially, it's a library in which they ask people to provide Riemannian metrics. So they have implemented like dozens of standard Riemannian metrics. And then they make all the job of going from this Riemannian metric to scikit-learn-like statistical estimators, like k-nearest neighbors, barycenters, geodesic regression, PCA, those kind of things. So it's a kind of standard library that takes you from your model to a working toolbox. Okay, and so I think it's work in progress for the last 3-4 years, but you can see that every year they add more and more things. And so it's becoming mature quite fast. Once again, all of those things were very cumbersome to implement before automatic differentiation. Now that we have it, we can start to dream a little bit more. Okay. So that's it for today, at least for the lecture. Maybe if you're interested, I'm just going to show you the website of JumpStat and all that. But I don't know if you have any questions or if you just want to take a break.